Now, to begin to answer the question what this is all good for, let's consider the following. First of all, this equation, if I've done the derivatives and everything correctly, is the result of this assumption that h of ty, and h of ty is our original function t cosine y plus 1 over y, has a derivative that's equal to 0. When does a function have a derivative equal to 0? When it's constant. So that this equation has a solution that is basically simply this function here has to be constant. We set this equal to constant, try to solve for y. That's difficult to do in closed form explicitly, but at least implicitly this would give us a function y of t anytime this is set equal to constant. Now we'll come around to that in a little bit here. For right now, here's our equation. Let's pretend we didn't know that it came from this function up here, which I've kind of hidden, not necessarily intentionally, just with this cup that the camera needs to focus on for the moment. Okay, here's the equation. Okay, I'm going to observe something about this equation. This equation is of the form, let's see if I've got room to this equation is of the form m of ty dy plus n of ty dt equals 0. Now, m of ty is this function, which is negative t sine y minus 1 over y squared, and n of ty is cosine of y. Now again, it's not real clear where this is heading, but I'm going to make an observation and then we'll see why it's true. Okay, m of ty has a derivative with respect to t, which is equal to what? Well, derivative of this with respect to t is negative sine y. Now, actually, I should write this as a partial derivative with respect to t. I'm a little careless with that. Okay? So, treating y as a constant. Now, y is implicitly a function of t. We're not going to worry about that right now. If we treat y as a constant, this derivative is equal to negative sine y. Now, I want to also look at partial of n with respect to y. What's a partial of n with respect to y? Well, derivative of cosine y is negative sine y. These are equal. Now, that could have been predicted, but you might or might not have noticed why. So let's go back and trace this out again. Where did m of ty come from? M of ty is this thing in front of dy, which was originally the derivative with respect to y of this function. So m of ty is dh dy. So let's just write that out so we can keep track of it. I think maybe we can get rid of this cup. M equals partial of h with respect to y. And we could call that h sub y. Derivative of h with respect to y. That should be a familiar notation. And n, what is n? Well, n is obtained when we multiply through by dt, and it turns out that n is partial of h with respect to t, which is ht, written in slightly shorter notation. It follows that derivative of m with respect to t is the derivative of h with respect to t and with respect to y. The second partial derivative of h of ty with respect to t and y. Now, you might see where this is going. Okay, mt is this, and y is what we calculated here. And y is h. Now, n is h derivative with respect to t. We're doing the y derivative of the t derivative. Or, well, it comes out the same thing. Because the order in which you take the partial derivatives, as you know from first year calculus, makes no difference. So that we have a situation that we can easily test. At least we know that if this equation is of the form h of ty prime equals 0, then mt and ny are going to come out the same as illustrated by what you see here. Is that an if and only if proposition? If this is true, does this have to be true? Turns out that within restrictions on the domain of the function and so forth, it's so.